Hello, we are Group 2 and here are the group members. We are presenting our project, the CO2 emission predictor. First off, let me talk about our objective for this project. Our goal is to train a model so it can predict estimated CO2 emission for a vehicle given its engine specifications and road test results. With this trained model, we expect that our predictor can help the public to determine if it is worth purchasing a vehicle or not in terms of eco-friendliness, considering the impact caused by its potential CO2 emission. Then what exactly is the problem we are trying to solve? Here is our considerations. First, it is supervised since CO2 emission is provided with label as the prediction target. Second, it is regression for the values in the target column being numerical. Third, it is fast learning because the model is trained only once with the given dataset and no more. And finally, it is model-based as the algorithm detects the pattern from the features in the dataset to build the prediction model. Now, let's look into the dataset. It contains 15 columns in total. There is a set of columns related to engine specifications here. For example, engine size, number of cylinders, and fuel type. There is another set of columns for road testing result, fuel consumption in city measured in liter per 100 kilometer, fuel consumption on highway with the same measurement units, and fuel consumption combined with 55% fuel consumption in city and 45% of highway with two different unit measurements. There are some other columns too, such as maker or manufacturer, if you can say, and the model, vehicle class, and so on. And finally, the target column, which is CO2 emission measured in gram per kilometer. Given this set of columns, our initial thoughts was that the engine size and fuel consumption in city are the two most impactful features on the target column. And this is our EDA graph showing the kind of linear relationship on the target with each of the features. As you can see, CO2 emission grows almost linearly as engine size and fuel consumption grows too. There is also a histogram to show the distribution of the values in each columns. As you can see here, some of the columns seem to not follow the normal distribution shape. Well, we will see later if those columns degrade the performance of our model or not. Before getting into the data training, there are some minor procedures we took on the dataset to be explained first. Initially, it has some dummy rows to explain what each categorical value stands for. For instance, the value X in fuel type column means gasoline. Those rows are dropped because obviously they are not needed for model training. Moreover, we also have some columns like transmission, make, year, vehicle class, and model. They are dropped as well since they are considered to have little or no impact on CO2 emissions. Also, combined fuel consumption MPG column is dropped too for representing the same value with the another one, just by different measurement units. After the data cleaning above, the dataset is scaled and encoded with standard scaler and one-hot encoder, and then train and test set are splitted with 20% test ratio. Given this pre-processed dataset, we conducted training with three types of model: linear regression, elastic net, and decision tree regressor. The grid search hyperparameter tuning is applied for all of them as well, and below is the result. Linear regression shows the highest R2 score of more than 99% and negative mean square error of negative 4.5. Therefore, it is proven that linear regression is the best performing model that we have. Then let's look at the performance metrics for a linear regression model. The learning curve shows a tendency that both training and validation error converges to mean square error of 4. Well, considering the shape of the graph, we can say that the model suffers from neither underfeeding nor overfeeding. On the other hand, the distribution of residuals, also known as distribution of errors, is showing the opposite perhaps. The p-value of this graph is almost zero, which is less than the threshold of 0.05, meaning this graph does not follow a normal distribution well. Given that it is generally true that a model performs well if its residual distribution graph follows the normal distribution, well, it seems that our model has some kind of problem. However, this graph has the explanation for that. As you can see, almost every predicted value has zero or very small error. Our interpretation of this fact is that the features of the dataset have near zero noise for their values to begin with. So naturally, the distribution of residues has to be very skewed to zero value and its vicinity. By this fact, we determine that our model is good enough despite the issue with the distribution of residuals. That concludes our presentation, and thank you very much.